today's video lecture, we are going to go through mainly two prepositions and one theorem. As if you all are familiar with the lecture notes of these prepositions and the theorem, but for a further clarity, we will see how precise we can be as we move on into the proof. So let's start with preposition 3.9, which says if we have three distinct points set 2, set 3, set 4 in the extended complex plane and three another set of distinct points w2, w3, w4 in C infinity itself, then there will exist only one Mobius transformation such that set 2 is mapped to W2, set 3 is mapped to W3 and set 4 is mapped to W4. So for the proof, it is a very simple proof. First we have to define or call the first cross ratio, that is the quadruple Z2, Z3, Z4 to be the function T of Z. We know that every cross ratio is a Mobius transformation which sends the uh, suppose if this is the second term, so the second term is sent to 1, the third term is sent to 0 and the fourth term is sent to infinity. That is nothing but T of Z2 is equal to 1, T of Z3 is equal to 0, T of Z4 is equal to infinity. And similarly, for the cross ratio quadruple Z W2, W3, W4, call it M of Z, and the same condition is satisfied by M. And also we know that the composition of Mobius transformation is in turn a Mobius transformation, and the inverse of a Mobius transformation is also a Mobius transformation. So we know that M inverse composition T, we are calling it as S, is also a Mobius transformation. And consider S of Z2. Okay, S of Z2 is equal to M inverse of T of Z2. T of Z2 we know that that is equal to 1. M inverse of 1 will be nothing but W2. Okay, so there is a little change there, that is nothing but W2. This will be W2, this will be W3, and the third one will be W4. W2, W3, and W4. Okay. So S is a Mobius transformation with the decide property. Okay. So we have to now prove that this is actually a unique Mobius transformation, right? So we are taking R to be another Mobius transformation such that R of set 2 is equal to W2, R of set 3 is equal to W3, and R of set 4 is equal to W4. So now we are going to consider, and here there is a small change here, that will be nothing but instead of M we are having S, right? S is our, okay, here that will be our composition S of, no, composition S of, or composition S of. Okay, so we are considering the Mobius transformation R inverse composition S, and we are calculating the image of R inverse composition of S of Z2, Z3, Z4, and we are getting them to be Z2, Z3, Z4 simultaneously. Okay, that means this set 2, set 3, set 4 are actually fixed points of the Mobius transformation R inverse composition S. And earlier, while we were dealing with Mobius transformations, we had said that the maximum number of fixed points a Mobius transformation can have is 2, right? So here we are having 3. That means we are concluding that this R inverse composition S, the map, is nothing but the identity map. That is the only possibility, right? Because no other Mobius transformation can have more than 2 fixed points. So we end up with a result which says that R is equal to S. That means the such Mobius transformation with the desired property is unique. So we proved the first preposition, preposition 3.9. Okay, as a note, we know that when we are dealing with geometry in R2, right, in the Cartesian plane, if you are given 3 points, you can definitely form a circle from those points. And suppose we are speaking about a circle in C infinity, and infinity, the point infinity is a point among the 3 points. Okay. So that circle will correspond to a straight line. Okay. Right? That is the only possibility for that circle. So when we are talking about circles or collinearity in C infinity, we cannot say that uh, we cannot talk about the term or the word which is non-collinear, right? So because like any 3 points, if you're given 3 points, you can form a straight line if one point is infinity, right? So that doesn't make any sense. So we won't usually use the term non-collinear anymore as we are standing in the extended complex plane. Okay. So the next preposition is preposition 3.10, which is a very important preposition. I know that you all are familiar with the lecture notes, but I think you should also move through the video lecture so that every logical movement throughout the proof is very clear. Okay, the statement says that if four distinct points are given in C infinity, then the cross ratio Z1, Z2, Z3, Z4, the quadruple, is a real number if and only if all the 4 points lie on a circle. Okay. So for that, we are thinking about Mobius transformation S from C infinity to C infinity, which is nothing but the cross ratio. S of Z is equal to the quadruple set 2 set 3 set 4. That means we have to prove that this cross ratio is real number, right? So instead of proving the cross ratio is real, we can say that S of Z is real. That is necessary for us. Okay. So that means the set Z such that the cross ratio belongs to R is nothing but the set such that S of Z is belonging to R, which is nothing but the set of all sets such that Z belongs to S inverse of the set of all real numbers. Okay, all of them are the same sets. Now we are claiming that inverse image of R infinity is a circle any obvious transformation. Okay, so for that, let S of Z is equal to a Mobius transformation A Z plus B divided by C Z plus D, and you know that definitely here the AD minus sorry, here the AD minus BC will be not equal to 0. AD minus BC not equal to 0. Okay. So if Z is equal to X, a real number, and if W is equal to the S inverse of this Z, then we can say that W is equal to S inverse of X, right? And then you can say that X is equal to S of W, definitely belongs to R because X belongs to R. And so since S of W belongs to R, we can say that S of W, the whole bar is equal to S of W, right? So from that, by using the definition of the Mobius transformation S of Z, you can say that AW plus B divided by CW plus D the whole bar is equal to AW plus B divided by CW plus D. Okay, and you are giving the conjugate property on the numerator and the denominator and then splitting, and you get this equation. And when you cross multiply and rearrange, you're going to get the equation number star sitting here. Okay. So now we are going to deal with two cases. The first case says that um, this term sitting here, right? AC bar minus A bar C. Okay, that is not equal. That is real. Okay, that is the first case. That is nothing but that is not. That is equal to 0. Because if AC bar is real, we know that AC bar, the whole bar is equal to AC bar. That implies A bar C is equal to AC bar. That means AC bar minus A bar C is equal to 0. So we are first assuming that this term sitting here, the coefficient of mod W squared is 0 or AC bar is real. Both are the same. Okay, that means the equation star can be rearranged into this because this is 0 that you are calling as double star. Okay. Now you're going to define 2 of alpha and beta, which is nothing but 2 times the coefficient sitting here is called alpha, and I into the coefficient here, the constant here is called as beta. We are naming them like that. Okay. Also note that this beta is nothing but I into BD bar minus DB bar, right? That is nothing but I into BD bar minus BD bar the whole bar, okay? And just for simplicity, z is equal to x plus iy and z bar is equal to x minus iy. So set minus z bar is nothing but x plus iy minus of x minus iy, and that is nothing but 2yi. That means I in 2 into I into the imaginary part of z. Okay. So here I have I into this. So you will have I into 2 into imaginary part of BD bar into I. Okay, that is nothing but minus 2 into imaginary part of BD bar. That will be definitely a real number. Okay, that is the observation we can make from there. Okay. Now the equation double star now can be rewritten in terms of this alpha and beta sitting here, and you're getting the equation sitting here. Okay, alpha by 2 W minus alpha bar by 2 into W bar minus I beta bar is equal to 0. So what we are trying to do is we are trying to find the inverse image of the extended real line, and we are trying to say that that will be either a line or that will be either a circle. Okay, so we have to analyze what this equation really means in complex analysis. That is also a basic fact we had dealt with while we were starting with complex analysis in our very first classes. Okay, so for understanding that, just consider this as a line. Okay, this is a line, and it is directed like this. You are having z to be an arbitrary point. It can happen from any of these any among the points on the line. Okay, set 2 and set 1 are fixed. Okay, so when we are thinking about set minus set 2 and set minus set 1, both of them will be in the same direction because set is sitting here. Okay. If set was sitting here, set minus set 2 and set minus set 1 would have been in the opposite direction. Okay. So in any ways, we can say that set minus set 2 into a real scalar multiple will be set minus set 1, or set minus set 1 is a real scalar multiple of set minus set 2. Set minus set 2 is a smaller vector here, right? So multiplying that vector into some scalar will give us set minus set 1. Okay, so I can write it as set minus set 1 is equal to some scalar s real into set minus set 2, that is equal to s set minus s set 2, and rearranging, you are getting z is equal to 1 by 1 minus s into z1 minus s divided by 1 minus s into z2. Okay, and call this 1 by 1 minus s to be equal to t, and just calculate 1 minus t, and when you and then you arrive at minus s by 1 minus s, which is the term here. So the equation which is sitting here can be rewritten as z is equal to t z1 plus 1 minus t into z2, and this is called the parametric form of a straight line in complex plane. Okay, and another, there is also another form. Okay, Here, when we were talking about the line here, this set minus set 2, right? This is a set minus set 2. This set minus set 2 is also a multiple of set 2 minus set 1 or set 1 minus set 2, right? So I can say that set minus set 2 is a real scalar multiple of set 1 minus set 2. That is also true, right? May the real number be negative or positive or whatever. According to our need, you can choose the positive or negative. Okay, so set minus set 2 is a real scalar multiple of set 1 minus set 2. So let that scalar multiple be m. Okay, and you're getting set minus set 2 is equal to m into set 1 minus set 2. And when you form it into the fraction, you get that is equal to m, and that is a real number. And like the earlier, we are saying that since this is a real number, the conjugate is equal to the real number. Okay, so you can use the property of the conjugate, and then rearrange and cross multiply and just cross out the similar terms in each sides. And when you do your steps, you're going to get this equation sitting here. Those are very simple steps. Okay, and on that equation, multiply it with I. Okay, so you get z into the term sitting here minus z bar into the term sitting here minus this term. Okay, so we are going to make it into the general form. Az plus a bar z bar plus b is equal to 0, where a is equal to the guy sitting here, and a bar is equal to minus I into z1 minus z2, and b is some real constant. Okay, this is the general form of a straight line in complex plane. So what we had while we were working out our proof is alpha by 2 w minus alpha by 2 w bar minus I beta, and that is the same form of line. And so we can say that, where you can say that beta is real or beta is a constant. Okay, so here we are getting it to be a straight line. Okay, and for the case 2, we are assuming that this AC bar is not real. Earlier we said AC bar is real. So as it is not real, the in the equation star, the first coefficient, right, AC bar minus A bar C, that is not equal to 0. Earlier we had that to be equal to 0. Okay. Then we define two of the gamma and delta, which is nothing but BC bar minus DA bar divided by AC bar minus A bar C, and delta is equal to minus of BD bar minus B bar D divided by AC bar minus A bar C. And when you just work it out, you can understand that this delta is also a real number. And the equation double star, it is not star, it is actually double star. Okay, sitting here. Okay, the double star can be rewritten as by dividing AC bar minus A bar C throughout, because it is non-zero. You get the equation like this, and you're going to substitute the gamma and delta, and here we have calculated gamma bar, so you know that the second coefficient here, that is nothing but gamma bar, and this one is gamma, and this is nothing but minus delta, because we had to count it as the negative of this term. Okay, so you got the equation like this. Okay, so when we are taking the three terms together, you get that is equal to delta. And now consider modulus of w plus gamma the whole square, that is nothing but the term inside the modulus into its conjugate, right? So you just cross multiply, take out the braces, and you're going to get this. And the three terms sitting here is nothing but delta. We had found it out like this. Okay, so you get that is equal to modulus of gamma square plus delta. Now consider, just keep in mind that we want to get a circle from here, because we earlier got the straight line. Okay, modulus of w plus gamma is equal to the square root of what we got here. Okay, and then what you do is just substitute this modulus of gamma square is nothing but uh, yes, that is nothing but gamma into gamma bar, and substitute for gamma and gamma bar and delta, and here I am just taking a 1 which is nothing but the dividing and multiplying with a bar c minus ac bar divided by a bar c minus ac bar, and note that this is nothing but the conjugate of this, because we need the same denominator that is happening for this term for this term also. That's why we are doing that. Okay, and then you're just taking out the braces, cutting out all the similar positive negative terms, and making the common denominator. Okay, and you can take the since this is square here and the square root, you can take one of it out, and the rest of them you just take the commons out, and that is raised to 1 by 2. Okay, and then you again when you do the proper steps, you'll get inside one term and its conjugate, and that is nothing but modulus of bc minus ad the whole square raised to the square root, that is nothing but bc minus ad modulus of bc minus ad divided by ac bar minus a bar c, and that is strictly greater than 0. And note that that is strictly greater than 0, since we know that Mobius, for the Mobius transformation, ad minus bc is always not equal to 0, so that will never become 0, and this is not equal to 0 obviously in this case. So what you arrive is where modulus of W plus gamma is equal to the constant rho, where rho is the guy sitting here. Okay, so this is the general form of a circle with center at a minus gamma and radius rho, positive quantity. Thus the result follows. So that is a very simple result, which is preposition 3.10, and that is very helpful for us while doing and dealing with the problems as well as theory of cross ratios. The next theorem is also a very important theorem, which is theorem 3.14, which says about the Mobius transformation always taking or mapping circles into circles. Okay, so it is also very direct proof. Suppose gamma is a circle in the extended complex plane and S be any Mobius transformation. Let set 2, set 3, set 4 be three distinct points on gamma. Okay. So definitely we know that S of Z2 is equal to W2, S of Z3 is equal to W3, and S of Z4 is equal to W4. We definitely don't know. We are assuming that they are mapping S Z2 is equal to W2 and so on. Okay. So definitely they are having images because it is a map, and here all will be distinct. That is a notable fact here, because s being an invertible function, it will be definitely 1 1, so all of the images will also be distinct like the pre-images. Okay, now consider the cross ratio set set 2 set 3 set 4, and we said that the cross ratio is not at all affected by a Mobius transformation. So what you do is apply the image here. That was a theorem we had dealt with, preposition 3.10. Okay, not preposition 3.10, a theorem which we had dealt before. So you get this, and this belongs to hope you are clear here, because this cross ratio is nothing but the cross ratio of the points of the images of these points itself. Applying S of Z, see here, S of Z2, S of Z3, S of Z4. Okay. Since this Z2, Z3, Z4 and Z, we are assuming that Z, they are all coming from the circle gamma. From the preposition 3.10, we can say that this cross ratio is a real number from the preposition earlier. Okay, that means this is also a real number, right? So we said that a cross ratio is a real number if and only if all the 4 points are coming from a circle. So definitely this S of Z, W2, W3, W4 all are coming from where? Some circle. So which and that let us call that circle to be gamma dash. Okay. So this is not the same circle, that is nothing but we can call it some circle. Okay, that is some circle gamma dash. All the 4 points are coming from gamma dash. That means W2, W3, W4 definitely determine a circle gamma dash. And so we can say that S of Z belongs to gamma dash for every Z belongs to gamma. Therefore, S of gamma is equal to gamma dash. That means every circle is mapped to some circle by the by any Mobius transformation. So that was the very simple and direct proof of this theorem, and hope you are now having a better clarity about the logical movement throughout the proof. So thank you for listening throughout this lecture video. Thank you.